Hello, hello. Don Geronimo, are you there? Hey, I can see you, but I cannot hear you.
Can you hear me now?
Yes.
Okay, we are live here in the OpenStack GDL. There's a lot of people. As you can see, it's a little bit dark here. Say hello. So, so you can notice that there is a lot of people. So we are already transmitting here. So please feel free to start when you want, and give us a little bit of who you are and what are you talking, what are you going to talk about, and so on. So a little introduction for this little talk. Okay.
Sure.
So
But
thank you for coming.
give me a couple of minutes because I need to test with you if you can see the slides over this link or not. So.
Are you going to share the slides?
That's what I'm going to try to do, but that usually winds up not working. Let's see. In theory, it should be just fine. In practice, now let's see what the practice looks like.
Did you send the slides? Yes, right? Did you send it to OpenStack GDL or .gmail?
I can send them, but there are a lot of effects on the slides, so I kind of need to project them. Let me see. I will send you a PDF after the talk, so you can share them with the group, but it won't be the same thing. Oh, it's funny. The commands are all in Spanish. Compartir pantalla.
That's it. That's the link. I'm sorry.
That's all right.
So you can learn a little bit Spanish, probably.
All right, let me try this other way. Where is my mouse cursor? Move it back here. And let's see if Google sees the deck now. Yes, it looks like it does. Maybe it's lying. Let's see. Can you see a slide that says cloud services?
Yeah, there is. We can see it.
All righty. Awesome. So it looks like it works. Do you see the title slide?
Yes.
Okay, perfect. Nobody touched anything. This is the strangest setup you can imagine. It's a Mac with OpenOffice. It's just brittle. All right. Okay, so ready to go whenever you want, Geronimo.
Feel free when you want. Please give it a little bit of introduction about you and what you do and what are you going to talk about a little bit. And that's it. Just start. And feel free to start when you want.
All right, let's go then. So my name is Federico Lucifredi, and I'm currently working at Red Hat, working on product management for Ceph storage. I pretty much spent my entire career in open source, save for a short period that I spent in academia. All my industry work has been in open source, which is a distinct privilege. I was the product manager for Ubuntu for the last few releases. I lost count of how many, but usually the one that I brag about is 14.04. And before that, so I was at Canonical for about 4 years. Before that, I was at SUSE for about 6 years. I was the systems management czar for SUSE Linux, which involved keeping a bunch of different teams in order so that the distribution could have good systems management tooling, particularly around upgrade. And a little bit before then, I was in the red carpet team at Ximian with Geronimo, and that's where our connection comes from. And I think that's quite enough about me. So this talk is just a little intro about Ceph. However much we can do in about an hour. I'm still quite new to storage. I've been in Linux for my entire career. So this is quite interesting because storage is a very broad and complex system similar to the kernel. So there is a lot of stuff to learn, and I really enjoy that part of the process. And the idea was to have an overview of how Ceph is structured. There would be a second part that we could go in another time, which is how Ceph is different. But for today, we'll just do how Ceph works at a high level. And one more thing is I was actually originally born in South America. And so my Spanish is extremely rusty, and I cannot deliver the talk in Spanish, for which I apologize. I still understand. So if at some point you have questions and you prefer to ask the question in Spanish rather than in English, that's fine. We can do that too. Okay, so without further ado, so when you're looking at the cloud, there are three key cloud technology choices. Ceph is in the storage box and is, in our not so humble opinion, the future of storage. Now, when you look at storing data, here is the past of storage. Originally, you would record information on stone tablets. Maybe there was a chisel there, then you have pen and ink. But today, it's much more opaque, and there is technology sitting between you and your data. This is one observation. Working through a computer means that we can store more information, and we can store it more quickly. But it also means that we have separated from the information that we've created. You cannot pick the bytes of a disk splatter with tweezers, so to speak. You need the hardware to decode it. You can see this maybe when you have data on RAID disks and your RAID controller dies and you didn't have a spare. Sure, the data is there because it's in copies on the RAID disks, but you only had one controller and you cannot get to the data. So this much higher density that computing enables for data storage also puts something in between you and accessing your data, something that, to use our metaphor, was not there when you were just looking at clay tablets or manuscripts or even printed page. You can just read them. So the whole point is that technology intermediates access between you and your data, and off we go. Second point. Everyone has seen a graph like this. This is what's happening to our data. There is a data explosion going on. Everything gets logged everywhere, and nobody throws away any data, regardless of how much information may actually be in it. So we have scary amounts of data. And here is the old way to store this data. You connect a bunch of disks to a computer, give humans access, multi-user OS, time sharing, all that revolutionary 60s technology. Of course, it looks rather like this as things scale out and you get lots of users. But then the result is that you need to scale up the system to keep up with demand. And here you see all the classic optimization problems. How can we make the same architecture do more kind of question? This justifies real expensive, costly hardware on performance grounds, and it is technically and economically broken in the face of the amount of data we are seeing today. But here is an alternative. Instead of making what you have today bigger, you take what you have today and add many units of it. Let's call that making it broader instead of bigger. This is scaling out, and the units remain as cheap as they were to begin with, but you multiply their number. And eventually, the industry figured out how to make appliances powered by this architectural model. You take lots of computers and lots of disks, and you put them in a box, and then you call it a storage appliance. You forklift it into your data center and plug in a cable. This is a storage appliance, an actual physical thing, something like this. And here is what's inside the typical storage appliance. The hardware is proprietary, not your typical Dell or HP x86 industry standard hardware. Then on top of it is software, also proprietary. And then you have your support and services contract. As an aside, here is a breakdown of the industry leaders' financials, EMC, from a recent 10K statement. $5.2 billion in support and maintenance. This is gross revenue. 1.1 billion spent in R&D every year. 1.6 million square feet of manufacturing space. So this is really a big business. What has happened since this model was most successful is that the cloud has started raining bits on CIOs' heads. We're here today because there is an inflection point and something has to change. So here is what we propose. We favor standard hardware that you already know and are familiar with. Open source software on top of that. Oh, there is a glitch on my slide. That's cute. Oh well. Open source software on top of that, and an enterprise subscription on top of that if you need it. It is optional as always in the open source business model. So standard hardware, open source software, optional services contract. But this is a different way of doing business. We want to look at the technology really. So that's where we go next. This is what Ceph is, a much more sustainable model for storage. That's how Ceph was built, purpose-built, to be over in the last, I believe it's now 12 years. This was not a hack. This was an academic project with a lot of research and funding from the national labs initially. So Ceph was purpose-built to power infrastructure, unlike many other distributed storage systems out there. So let's look at how philosophically Ceph was designed first. First, we wanted it to be open source, and it is the best way to get technology into the hands of people who can use it quickly. Secondly, we wanted this to be community-focused open source. This focus has resulted in an unusually vibrant community for an enterprise product like storage. Technically, we wanted it to be scalable, and in the scale-out fashion, not the scale-up model. When you are, I have a colleague that likes to say that when you are organizing a big conference, like here today we're at OpenStack Vancouver, we have 7,000 attendees. When you want to scale out the number of people you have around here, you don't look for a bigger hotel, you look for many different hotels. And that's what the comparison between scale out and scale up really looks like. Part of being scalable is having no single point of failure in a scale-out design. Ceph has none. Most importantly, Ceph was designed to be self-managing. Lots of distributed storage systems require operator intervention when something malfunctions. You cannot really accept this constraint when you have a large distributed system. You cannot raise a flag saying, pay attention to me every minute, because in a large system with tens of thousands of nodes, issues are the new normal. There is always a broken hard drive somewhere that needs to be replaced. There is always some data that's being replicated as part of that recovery. And obviously the administrator cannot be paged for every single one of these things. Now give me 1 second. I'm having trouble with changing the slides here. What is going on? Right. And we go here. Oops, not that way. Geronimo, can you still see the slides?
Yes, we can see the slides. It's
philosophy, design, and cross. Is that correct?
Yes. Yes, philosophy and design.
Okay, good. Just give me 1 second. Okay, all right, let's continue. So where were we? So we're on self-managing, the point that the system needs to manage itself. When something goes wrong, requiring operator intervention is just not okay. And that's also when things go right, when you keep adding hardware to the cluster, and the placement of your data needs to change, needs to rebalance. That's also something that needs to be transparent, because you have to assume that it's an operation that's happening all the time. Look at Yahoo was announcing that they're going to use Ceph as the backend for their object storage, beginning with Flickr. That's going to be tens of petabytes of data, and Yahoo is planning to add them by the cluster, not even by the rack. This kind of operation requires minimizing the kind of manual intervention that administrators need to perform. All right, so that's for the philosophy. So after 8 years really at the point of this chart, and thousands of commits later, we got Ceph. Inktank was launched and then acquired by Red Hat less than 2 years later, which brings us to today. So this slide is the 50,000 feet view of what Ceph is. As I was saying when I introduced the topic, it's really a broad subject, which is why it's so interesting. At its core, Ceph is a reliable object store that is intelligent and takes action independently of human intervention to replicate data when there are failures, and to replace data when it needs to for balancing. This abstraction, which is called Rados, is presented to data users in three ways. It's a distributed storage cluster with three interfaces. If you need object storage, use the Ceph object gateway. For block, use the Ceph block device. And for the traditional POSIX file system interface, you can use the Ceph file system. That's the very high-level view. Let's dig in. So here are the interfaces into the Ceph cluster with the original technical names, less brandy, unlike the previous slide. So here you see that Rados GW, also known as RGW, is the object gateway that we were calling in more marketing terms in the previous slides. And RBD, Rados block device, is the Ceph block device of the previous slide. So with that out of the way, let's start with Rados. Rados is a distributed object store, and it's the foundation for Ceph. On top of Rados, the Ceph team has built three interfaces that allow you to store data and do amazing things. But before we get into all that, let's start at the beginning of the story. Rados is a reliable, autonomous, distributed object store comprised of self-healing, self-managing, intelligent storage nodes. And here is how it works. If I have 5 disks, these could be spinning media, could be solid state, could even be RAID volumes, but that is typically not a good idea and it's unnecessary. We have file systems on top of those 5 disks. Btrfs, ext4, and xfs are the ones we support currently. XFS is recommended while we wait for Btrfs to get there, by the way. And then you have 5 OSDs, object storage daemons, 1 per disk. This is a software layer that makes each disk part of the Ceph storage cluster. It is a simple piece of software. You configure it with a path, and it exposes that path as a storage location to the cluster. And that's our representation of the cluster. So let's start looking at that. And you, of course, interact with the storage cluster as a whole, and not as single logical units, not as a series of hosts. You're talking to the cluster. So here is a depiction of what could be a Ceph cluster. We have 3 by 3 by 3, 9, 3, 6, 9, 12, 15, 150, looks like 135 nodes. And you see that that 3 of those nodes are different. So let's look at that. If OpenOffice doesn't crash. Oh no, it works. Yay. All right. So in the previous diagram, we had 2 types of cluster members. The blue box with the red bar represents an OSD node. Each OSD provides access to a path in the cluster, usually a disk. This is a component that is responsible, the component that is responsible with providing access to the data. It is also responsible for peering with other nodes in the cluster to replicate data. When a drive fails, recover at control cluster state. Geronimo, are you pinging me? I think I hear messages.
Hola.
I can hear you.
Okay, sorry. Okay.
Is everything going fine?
Yeah, something is... Okay, can you continue?
Sure.
We missed it. We missed the link that you were sharing.
What did you miss?
The share screen.
Oh, okay. No, that I can turn back on. I thought that you were sending me messages on Google Plus, and I needed to check.
Sprichst du Deutsch?
If you can see me, that's fine. I can resume.
I can see you.
Perfect. All right, except that I put up the wrong slide.
Can you share?
Can you see the slide with OSTs and mons?
No. Can you share again?
Okay. Let me try something else then. Let me check what's going on here. Okay, so I need to first put technology. It's funny, there are so many slides in this presentation that it takes a while to load even. Okay, so now I'm back on the right slide. Right, and screen share. And this one. Okay. Can you see it now?
Yes, we're there.
Perfect. Did you lose any of the slides while I was talking, or was this the last one that you have seen?
Yeah, that was the last one that we are seeing. We are seeing like the monitor and the new ones. That's it.
Perfect. All right. All right. So let's see. Whoop. There is something going on with my computer now. Sorry. This is getting frustrating. One second, let me fix this.
Nothing?
I think OpenOffice is suffering under the weight of this presentation.
Can you share the presentation with Google Drive or something with OpenStack gdl.gmail.com or something? So at least.
Let me try again. I think I can just restart LibreOffice, and that should
Okay.
resolve whatever is going on there, or so I hope. Let's see. Too many animations in the stack. Okay. Let's try now with. Hmm.
There.
Okay, let's try resuming. There is something strange going on with the slide software, but hopefully we can make it to the end without more incidents. So in the previous diagram, we had two types of cluster members. We had, let's see, we had, oh, no, it's not. All right, we had 135 or so cluster nodes, and 3 were labeled differently. So this is not working. Slowly.
There.
All right, so in the previous diagram, we had two types of cluster members. The blue box with the red bar represents an OSD node. Each OSD provides access to a path in the cluster, usually a disk. This is the component that is responsible with providing access to the data. It is also responsible for peering with other nodes in the cluster to replicate the data. When a drive fails, recovery is also performed by the OSDs working in peer-to-peer fashion to replicate and rebalance the data. Monitors instead control a cluster's state. They know the state of each node at any given point in time. You generally want an odd number of monitors and a small number because they vote using paxos under certain circumstances. And critically, so if you have many of them that need to come to an agreement, you're slowing down performance. So generally, you have 3 nodes, 3 monitors. You have 5 monitors when you have a really large cluster. But otherwise, there isn't a reason to have to add monitors too much. So keep the number down for performance reasons, and critically, the monitors are not part of the data path. Writing or reading data does not involve the monitors in any way. So it's not a scalability issue. You want multiple monitors for HA purposes, not scale. So that's what Rados is doing underneath. All of Ceph is built on this underlying layer. The useful applications are built on top of it. Starting with Librados, that provides you with native ability for storage and data retrieval straight from the Ceph cluster. This is not REST-based or anything like that. It is a fast native protocol. It provides you with fast, direct access to the Rados cluster with through language-specific bindings. So the trade-off here is that you're really interfacing straight into Rados, but you have to write your own programs to do so. So we have some users and some customers that do this. They decide that they're going to store the data in Ceph, and so they don't mind the fact that they're going to write a new application straight through this interface. And there are some advantages, but obviously this interface only works with Ceph. The other interfaces, like RGW, the Rados gateway, provide more standard interface to the storage. Hello there. So RGW provides a liberator's interface. It sounds like we need a mute. Okay. RGW provides a liberator's interface on the southbound side, but a REST interface on the northbound side to the application, specifically in the form of support for the S3 and Swift storage protocols. So this gateway, this daemon makes the cluster look like Amazon storage if you're using the S3 protocol, or like Swift storage, and you can use that to consolidate storage in Ceph in an OpenStack configuration. So RGW essentially is an object store proxy. It's a thin layer translating REST to a direct Rados call. It then uses Rados to store or retrieve data, but using the semantics of S3 or Swift when talking to the client. It also integrates with Keystone for authentication in OpenStack clouds, and it supports buckets, accounting, and the usual trimmings of an object store. Next up is RBD, the Rados block device. This is the most immediately interesting one for those of you standing up clouds. Here is how it works. If you have little bits of a volume spread across the cluster in 4 megabyte chunks, RBD will link those into the virtualization layer, into KVM, and present those as a single disk. Striping a volume across the cluster in this way, RBD provides the illusion of a single volume to the virtual machine. It also can provide NFS, Ganesha, and Samba interfaces to other users. This is quite interesting. I'm waiting for the next slide. This lets us do interesting things. As the storage is not directly attached to the VM anymore, we can suspend on one physical hypervisor and restore on another. And if your hypervisor supports it, you can live migrate a VM because the storage doesn't need to move. Another interesting trick that RBD can perform is through a kernel module, KRBD, which has been in the upstream kernel for a while now, 2.639, I believe. It mounts an RBD volume as storage. You can then mount in dev, run mkfs operations on, and treat just like a normal disk. But it is actually distributed on your cluster, giving you parallelism on your reads and replication of data, protecting you if one of the drives fails. A very robust way to store disks. So the Rados block device, storage of disk images in Rados, decouples VMs from hosts. Powerful concept as we described. The drive is striped across the Rados cluster, across the storage pool to be exact. And you can snapshot these virtual images, operate in copy on write mode. Ultimately, and I'm sorry, I'm rushing here. You can perform snapshots on these images, and you can do thin provisioning or or other things that usually benefit from copy on write. Ultimately, you could say that RBD is responsible for Ceph's success. 44% of OpenStack deployments, as of the data that the foundation gave us here yesterday, use Ceph RBD for storage, more than any other technology. Use Ceph RBD for block storage, I should be precise, more than any other technology. This is primarily because Ceph integrates seamlessly with Cinder, with Glance, and with Nova to provide ephemeral images. And as we were saying before, RGW can provide the Swift compatible interface. So the success of Ceph is predicated on the fact that you now have the ability to have all of these different types of storage coming from a single cluster. So you have a single silo of storage, and that is operationally quite a simplification from having different hardware or different systems for different pools of storage. And it also makes your provisioning considerations simpler. You just need to add storage. You don't care what type of storage it is. It will just be consumed whichever way your cluster needs to consume it. So if you need more block, it goes out as block. If you need more object, it goes out as object. With traditional systems where you have different types of storage coming from different parts of your data center, you have to build out those independently. You have to do capacity planning exercises for those independently, and if you get them wrong, well, you have hardware sitting on the wrong side of your racks. The final component is the Ceph file system. This is the one that is least mature at this point. It's the only component that is not currently production ready in Ceph. This is ironic because I believe the project actually began working on a file system, but block and object took over, and they got to being production ready much sooner. So the final bit that we have is the file system. This is something that is going to reach maturity soon, and it provides a distributed, horizontally scalable POSIX-compliant file system built on top of Rados. So this is an important difference as opposed to you taking a volume out of RBD and then partitioning it with a file system. And that is fine. That file system is striped across your cluster, but it doesn't scale the same way as the file system would. If you really want a horizontally scalable file system, this is the component that we need to fetch. So how does that work? So file system metadata is stored in the Rados cluster, just like any other data. And then we need to introduce MDS, the Ceph metadata server. Here is represented with these new squares, which have trees in them. Clients accessing files on CephFS first make a request to an MDS, which provides what they need to get files from the right OSD directly, not through the MDS. So the cluster knows how to find data, but when you have a file system, there is a lot of associated metadata, directory trees, for example. And so the MDS gives you a centralized point to control these operations. What is important scalability-wise is that the client never goes through an MDS to retrieve data. it just goes to an MDS to retrieve file metadata that has very different performance characteristics from the other, from the alternative. Now, 1 second, waiting for the slide here. Will it, or will it? Oh, no, it crashed. Alrighty, 1 second, I need to reload it.
Don't worry.
Okay, slide 38, I think. Looks like running Google Hangouts and LibreOffice with a lot of animations on the same machine is a little bit of a heavy workload.
Okay, we can see your screen. There is.
Do you see the client slide?
Yes.
Alrighty. Okay, so we were saying file system metadata is stored in the Rados cluster, just like any other data. Then we have introduced MDS, the metadata server, that gives us what we need to provide the illusion at this point of a file system, because data is not really stored that way to the cluster. Just like the monitors, the MDS servers are not in the data path. This design allows management of all the metadata required by a file system to happen in a single logical unit, and enables scaling out the metadata service, just like our architecture requires. And so the metadata server can do the job of giving everything that's needed to build the file system abstraction. By the way, if you're not running a Ceph file system, this daemon, this service does not need to run. This is just for completeness. As I was saying right before the thing crashed on the last slide, this is actually the only part of Ceph that we're still working on to reach production status. So CephFS is actually reasonably reliable. There are plenty of users out there. It's not the file system that we're working on. What we're working on is the utilities that you need to do recovery and maintenance of the file system. So currently, for instance, there is no way to do an FS check of a Ceph file system. And some of you that might have run this file system that used to be known as the Riser file system will remember how wise it was to run a file system with no good FS check tools. So we're not recommending to use this for production until we are ready with proper FS check and equivalent recovery tools. But the file system itself is not where the bulk of the work is going. It's going into these tools. So this is kind of the first 40 slides of a very long talk. This is how Ceph works. And the second part would be to go over how it is different from a traditional storage system. So there are some obvious questions as to how it manages to be different, and some less obvious that maybe if you guys want, we can do in a future session in the fall or whenever you have time. But for today, I would stop here. Did it make sense despite the interruptions? Was it useful?
Yes, it makes sense. I think I don't know if there is any question here in the audience. Let's see. Let me just ask the audience. Anybody has any questions? Daniel, can you come here? There is some question here.
Hi, Federico.
Hello, sir.
Do you have any kind of metrics or something like the time that it goes to access the disk or something like that, the transactions, or how much time it's taking for doing a transaction or something like that?
That is a good question, and it has a very broad answer. The way we usually split the problem is by looking at queues. Broadly, in the generic sense, there are just too many answers. The performance of the cluster of of software-defined storage in distributed clusters is remarkably good. As is proof the fact that you can actually back your OpenStack cloud with it, and that about half of everybody out there is doing it with Ceph. But performance questions are really hard to answer because of all the layering and all the complexity that the system has, and all the smarts that it has to react to anomalies. What we are doing as Red Hat is that we're trying to publish white papers for different types of use cases. So there is some data that I believe we've published for the RGW interface. We're working on updating that so that we can compare the release that is coming this summer, the one based on Hammer, the upstream release that was just cut last month. We're trying to create benchmarks so that we can show a comparison between that and what the performance of the previous supported release was, Firefly. Similarly, we have different set of benchmarks for block. So it's very hard to answer just what's the latency or what's the performance, and then there are always the sub-questions. If you were looking at files, well, what if I'm doing many small files or a few large files? Or what if I'm doing many large objects? Or I'm sorry, if I'm doing large objects or many small objects. Similar things. So there is no simple answer to that. It really depends on what the use case is.
Okay.
If you send me an email, I can point you to, and you tell me what the use case is. I can tell you whether there is published data on that already, or if it's something that's still pending.
Yes, I think that will be useful if you can just send those links later. That will be fun.
Yeah, I will send you the slide deck. I will send you the slide deck so that you can share it on your Google Plus page or on the event website, or maybe I can post it to your event page. I don't know if I have if I can do that or not. Either way.
Here's a general question, Federico. Why XFS is recommended over the other file systems supported?
So Btrfs hasn't reached a state where we are ready to recommend it in production. So we have been waiting for Btrfs for a while. We really want to use Btrfs. It has many things that make it interesting, but it hasn't gotten there. There is some hope now that I believe Facebook has hired Chris Mason to finish the job, so I think that there might be some movement coming there, but until it's production ready, that's why we're not recommending ButterFS. And XFS is just a simple default choice for large volumes. It's what Red Hat recommends. It's what SUSE recommends. It's generally what we use for enterprise volumes. I think ext4 would be just fine, but XFS is better.
Okay. Any other questions here? So, how is this different from Swift? Why do we implement Ceph over Swift or instead of Swift? Or what is the difference? I noticed that Ceph can interact with Swift or Cinder or something like that. So,
that's right.
Why did we choose Ceph over the other technologies?
So it's an interesting, and this one is also a very good question. So Swift is the storage technology that comes as part of OpenStack. And unlike all of the other services in OpenStack, it doesn't have clean separation between the API and the implementation, which is unfortunate. But it will be fixed at some point. That is one thing. Second thing is Swift is only an object service. Ceph is block, object, and at some point file. So if you are putting your storage in a Ceph cluster, you are able to back all of your services, Cinder, Glance, Nova for ephemeral images. You can provide the Swift service even though Swift is not running. Ceph will show a Swift compatible interface. And in the future, as CephFS gets integrated into Manila, you would also have file system as a service. And this would all be backed by the same storage cluster. So that's
Wow,
what Ceph can bring to the story, while the Swift part is, Swift is entirely fine, but Swift is only an object store, so it can only do one of those things. It's fine for you to run Swift alongside other types of storage, but then you give up the advantage of having your storage in a single cluster. You would be running, let's say, a Swift cluster for objects, and you could run a Ceph cluster for block, and you could just go whole hog and run a cluster for a cluster for files, and then you have a collection of different clusters. So that's whether you want to look for consolidation or not.
Okay, here's another, Federico. Thanks for answering that question. But other than OpenStack, can I use Ceph in a different project just for cluster object storage, something like that, or is just created for to be used under OpenStack?
Oh, you guys are very good. You're hitting all the key questions. Yes. So about 70% of users right now use Ceph as part of OpenStack. But Ceph is general purpose storage. There is no rule that says that you need to use anything in OpenStack, and we intend to keep it that way. Ceph is a general purpose storage solution. The biggest area where we are making an impact outside of OpenStack is the other approximately 30% of our users. They are using Ceph to provide object storage to development teams in their corporate environment, specifically S3 object storage. So their developers are writing custom applications that consume an Amazon Web Services like S3 interface, and it's coming out of the Ceph cluster through the RGW gateway.
Do you have any kind of a small how-to or some kind of small application or something to show for people here to start like right now or something in an easy way, like the simplest hello world kind of for people to share?
So there are instructions to set up Ceph. I must admit it's not as easy as I would like, especially as someone coming from Ubuntu. I'm kind of a little bit obsessive about making things easy. So that's something that I'm working on. We're trying to streamline the installation process. It's not easy because distributed systems are messy to install, and I don't need to tell you guys. I mean, you are an OpenStack group, so you know that firsthand. For Ceph, it should be simpler than for OpenStack, and I want to get us there as soon as possible. So you will see some work around that in our coming releases. In terms of developers starting, I would say that there is going to be a white paper that I saw we're working on internally that would be a how-to on how to set up a demo environment on Amazon Web Services. So it won't be the highest performance Ceph cluster that you can build, but it will be easy for you to just spin it up by starting up 4 guests on Amazon AWS and running it there. I'm writing another one myself, which does the same thing on DigitalOcean, and I'll try to get that out at some point in the next few weeks. I can share the link once I have it done. There is also a book, Learning Ceph by Karan Singh. It's published by Pact Publishing. It's the first book on Ceph. It is not perfect, but it is very good material to get started, and it gives you several ways to install the system. So I would say those are 3 ways that you can go with.
Okay, we know that there is another file object or file system storage called cluster.
That's right.
What's the advantages of Ceph versus cluster? I know that right now most of the users of OpenStack are going towards Ceph, but some of them are using cluster FS. So can you tell us more about those technologies?
So this is a complicated one. It has 2 aspects. One is technology, and the other one is time. So let's start with time. As I was saying earlier, CephFS is not ready for production use, and we at Red Hat have been working for quite a while on making Gluster an enterprise class file system, to the point where now Facebook is using it for parts of their storage tier. Gluster's bread and butter is serving files, and it is ready today. So the most obvious thing for someone looking for file storage is to use Gluster. Down the line, when Ceph also starts providing files out of the same storage silo that you're using for block and for object, then it will make more sense to look at use cases and see where maybe performance is a concern, and on some types of workloads maybe Gluster performs better, while on others Ceph performs better. But today the simple reality is that CephFS is not done, Gluster is done, and it's there today. So I would say that's where we are today. Where we're going to be in the future is when CephFS is ready, we're going to make CephFS available through Manila services in OpenStack, so that you can continue having OpenStack storage as a single silo. You don't need to run multiple storage solutions for different services. But outside of that, it may very well make sense for Gluster to be used in certain types of workloads and for Ceph in others. And one thing that's very clear today about software-defined storage is that the performance analysis of how workloads perform in clusters of certain sizes or of certain layouts is something that there is a lot of work for vendors to do footwork around. It's clear that Ceph and Gluster work. What people need access to are simple recommendations like, well, if I build a cluster like this with Ceph, how many block IOPS will I get? If I build a cluster like that with Gluster, how many file operations will I get, and so on. Red Hat has been trying to publish as much of this as we can generate. We have 2 different performance teams working on it, but because it tends to be use case based, there are a lot of use cases, and the technology changes. So what we do also needs to be updated.
Okay, thanks. Here's another question.
At what point in the future will ZFS be supported in Ceph?
Aha. Well, let me see. I need to go find someone from Oracle. The problem with ZFS, I don't know about technical issues. The issue is more of ZFS being in the Linux kernel. I believe that that Oracle has licensed the shim so that ZFS is still under the original Sun licensing community license, I think it was called. Vendors other than Oracle have not been willing to merge in ZFS under current licensing. So the issue is more of bringing ZFS to Linux than one to bring Ceph to ZFS. I really don't have an answer there. It's TBD. It depends on how the politics around licensing evolve.
So it's about licensing there, right?
Yeah, it's about licenses and licenses around the Linux kernel, not around Ceph.
Okay, let me see here.
Actually, I misspoke. It's licenses around ZFS and the Linux kernel.
Okay, here is another question. Just wait for here.
Hi. Is there a way to do easy partitioning depending on the performance requirements, workloads, or anything like that? Like having different subclusters, let's say.
You mean some simple performance guidelines?
No. I mean, what you were discussing about is just having a single cluster. All the data is spread across all the different disks or whatever you have. But what if you have different technologies? Can you split the cluster into?
Oh, I see. I get it. Yes. So we have in Tech Preview, we have storage tiering that is meant to allow you to put data based on heat of data, so how often it's being accessed in different storage pools, so that you could technically have a tier with a tier that is SSD backed for your very hot data, and another tier that's backed by spinning media for colder data. It's still in Tech Preview, but that would automate migration of the data. You can also you can also already today just create different storage pools in the cluster backed by different technologies, and that is not limited only to the storage medium. It also includes the way you encode the storage. So we didn't go into the details of how data is replicated. The default is to have 3 replicas of the data across different nodes. But there is another way that you can encode data, which is called erasure coding. And that is interesting if you have really lots of data, because instead of requiring to multiply the amount of data that you have by 3 when you look at how much hardware do you need, you only need to multiply it by 2.2. It imposes a performance overhead. It's not as fast, but because it cuts down the amount of storage you need on tiers that don't need maximum performance, that makes perfect sense. And that is production ready today, and as a matter of fact, Yahoo's Ceph supercluster is using erasure coding. That was the primary reason for Yahoo to adopt Ceph. They didn't want to implement erasure coding on their existing object store.
Okay. Well, there's another question. I know that Ceph is a general usage. What are the minimum requirements from operating system, probably, and what is the recommendation for storage, like these drives or something like that, like to have a minimum working project?
If you just want to run it to learn how the system works, as I was saying before, you can use cloud nodes, and the performance will be quite adequate. I have my personal Ceph cluster running in DigitalOcean, so that when there is something new that I need to try, I can do it out of there. I know other people that have gone as far as building Raspberry Pi Ceph clusters. So it's you can go pretty low on the hardware. I would say the general hardware recommendations is that you want to have 1 gigahertz of processor for each OSD daemon that you run, and you would want to have 10 or 40 gigabit Ethernet networking for a production setup. But that is very different from the Raspberry Pi scenario. So one thing is you're trying it. There is no traffic on this network or on this cluster. You can use pretty much anything you want. If you want to go to production, what we recommend is 1 gigahertz per OSD, 10 or 40 gigabit Ethernet networking, and well, if you can use SSDs for storage, that would be awesome. SanDisk has built this storage array that is running Ceph in hardware that's called InfiniFlash. It is just unbelievable, the kind of performance that they can get out of that cluster. But it also costs a little bit more than 4 Raspberry Pis.
Okay, thanks. Let me see if there's another question here. Seems no more questions about here. No more questions? No?
All right,
Thanks.
guys.
Thanks a lot. I don't know.
Thank you for having me. It's a pleasure. And I'll send you the slides for the page. It may be the weekend before I send them, but I'll try to pack them up and send them off tonight. Okay, we appreciate that, and thanks you for your time, Federico. How is the OpenStack Summit going, by the way? The keynotes were boring. I was disappointed. I was expecting some pizzazz, instead it was just boring. But the talks are fine. So I had some work to do today. I'm looking forward to hearing more talks in the next few days and have some training on Friday. Okay, sounds fun. Okay, thanks a lot. I know we appreciate your time.
And thanks a lot for participating with us. And let's hope that this is not the first time or the only time. We expect. I don't know if we really enjoyed that you can share with us your knowledge or your recommendation about Ceph, and we expect this is not the only one. We expect looking forward for another one probably in the future.
Sure.
But thanks
It's
a
a
lot.
pleasure. Hasta luego.
Hasta luego, bye. Thanks a lot, man.
See you soon, guys.
See you soon.